Hi everyone. I'll just request everyone to mute themselves so that there's no background noise. Cool. So what we're going to talk about today is we are going to talk about like essentially the life of a GraphQL plus minus query in Dgraph. And I want to just walk through some examples and show how those queries are executed and what happens if you have multiple alpha servers and if you have like a cluster of say like 7 to 8 nodes or something, then how does how does it work? So we'll just go through a basic example first, and then once we have gone through it, we can go through more complicated examples, or you guys can ask me any questions about anything that's not clear, and we can take it from there. So what I have here is I have a cluster of dgraph in which I have 3 groups. So I've just drawn it here, and then we'll use this cluster. Like once we understand this cluster, we'll use this cluster to see how a query would be executed. So we have group one, which has A1, A2, A3, which are all alpha nodes, and then we have group two, which is A4, A5, A6, which is again like 3 alpha nodes, and then we have group three. So essentially in dgraph, what happens is you have different groups, and different groups have data for different predicates. And within each group, you can have multiple alpha nodes. You have group zero, which only has zero, which is used for essentially handing out timestamps for transactions and UIDs. So that's what zero nodes are used for. And then you have alpha groups, which which is where all the data is stored. So what I have here is I have group one, which has data for a predicate called name. And then I have group two, which has data for director film and for initial release date. And then group three has data, say, for Netflix underscore ID. Uh, so for example, what we are talking about here is a scenario in which you have multiple alpha nodes and you also have multiple groups. You could of course run dgraph alpha on just one machine, and then you would just have one group and all your data would lie on a single machine. But if you were to increase the number of alpha nodes that you have, and if you were going to have like more alpha nodes and more groups for sharding and replicating your data, then you could end up in a scenario like this. So one more thing here. Uh, are there any questions?
Yeah, Pawan, so there is only one group for zero, always?
Yeah. So essentially, like all the zero nodes are part of group zero.
Okay, cool.
Yeah. So you could have 1 0 or 3 0, 5 0. All of them would be part of group zero itself, because all the zeros have the same information. The main reason that we have groups in alpha is because we want to shard data among the groups, but all the nodes in zero maintain the same metadata information. There is no sharding or anything that happens for the data that is stored in zero nodes. So we just have one group.
But then what will be the point of multiple zeros?
The point of multiple zeros is that you should have fault tolerance. So you should have like for example, if 1 0 node goes down, you should still have other zero nodes which
Okay,
can still hand out timestamps. Yeah.
cool. Okay.
Uh, so what I was talking about is that if you see if you see any nodes in a group A1, A2, A3, what's happening is that all of them have the same data. So for example, like these 3 nodes which belong to the same group would have data for name. And the idea there is that if one of the node in a group goes down, then you can still get all your reads accessed through other nodes. So it's again like the point is fault tolerance there as well. So if you had like the reason you would have more nodes is to have more fault tolerance and to be able to also serve more reads faster. So you have more replicas. That means that like a request for a predicate can go to any node in the group. Yeah. So I think now what I'll talk about is with this kind of infrastructure, if you had a query, so we'll see a query and then we'll see how that query is executed. So I've opened the docs here and we are going to go through this query, which is the query I have here, in which I'm asking for name Blade Runner. And then I'm saying that give me the name, initial release date, and Netflix ID. So what we want to see is that if your data is stored on different machines and if you have different groups, then how would this query be executed? So for example, what would happen here is that now that we have this query, we'll just see. So say you got the initial request from group one, and then the initial request says that give me all the entities which have name Blade Runner. So because data is stored on group one itself, it would locally execute the query. So it would use the indexes that Dgraph has, to find all the entities which have name Blade Runner. Once we have that, then if we want to get like the initial release date of all the entities that have name Blade Runner, so then what would happen is that group 1 would send like a gRPC request to group 2 to essentially like it could be sending the request to A4, A5 or A6. It could be sending it to any of the nodes in group 2 to be able to get the initial release date for all the entities which it found at the root. So it found a bunch of entities which had name Blade Runner at the root, and then it makes a request to group 2 to get the initial release date. Similarly, because Netflix underscore ID is also something that we requested, and that lies on group 3. So group 1 would also make a gRPC request to group 3 to get the Netflix underscore ID of all the entities which have the name Blade Runner. And like if you're asking for some data that already lies on group 1, like the name, it would just be resolved within the node that got the request. Otherwise, if that node doesn't have that information, it would know which, like it would know that which group serves that predicate and what are the like what all alphas are there in that group. So it would just send a request to one of the alphas in the group, and then that's how a request is resolved within Dgraph. So this is a simple example. We'll also go through a more complicated example. But some of the things to note here is that we only make one network call per level. So what I mean by that is, if I had like a bunch of IDs that were resolved, so say I'll just draw it out here. Say if I had like a filter like any of terms, name Blade Runner. So if I had something like this, and this returned like UIDs 20, 21, 24, 25, and say I basically had a child call, give me the initial release date of all these entities. Initial release date. So in this case, we would just be making one network call to fetch the initial release date of all these IDs. So one network call to fetch release date. And that's because all the data for a predicate lies in one group. So because we do sharding by a predicate, we can give it a bunch of UIDs and say that give me the value for this predicate corresponding to these UIDs. So give me the initial release date for all these UIDs 20, 21, 24, 25. So essentially we would be making one network call for resolving one level. And that means that what would happen here in this example is that for getting the name @en of all the entities which were returned at the root, we make one network call. And this is the maximum. We could be making lesser network calls if the data lies on the same machine. And again, for getting the initial release date of all those entities, we make another network call. That's the maximum again. And then for Netflix underscore ID also, we make one network call. And the good thing about this is if the root, say for example, this root function returned like essentially a bunch of UIDs, say 100,000 UIDs. Still, we would not be making 100,000 calls to get their name, initial release date and stuff. We just make one call. So that's one thing. And then another thing that happens is that all calls at the same level happen concurrently. So that means that we would get the name, initial release date, and the Netflix ID. We would be making those calls concurrently, which means that if that data lies on multiple machines, we make those calls. We make those network calls concurrently, and like because it's a network call, so essentially we are not using much CPU. We can do all that stuff concurrently and make sure that that essentially whatever query we have, it is executed efficiently, and then this thing happens recursively. So if I had more children of a child, again all of those would be resolved concurrently. Are there any questions here at this point?
So
Pawan,
I have
one question I have that
Yeah, go
so
ahead.
if there are like the number of this is more of a Go lang question. So I saw this that we use Go routines like we spawn a new Go routine for each predicate in that particular level. So
Yep.
so if there are like a large number of predicates, but like does it have like a limit to how many Go routines, like how much parallelization you can? Is there a limit to that, or I mean,
We don't have a limit to that. We like that's something that's just left to the Go scheduler to kind of figure out that if it can execute more Go routines, or it can or it should wait before the existing Go routines are already like scheduled and executed.
Okay, so yeah, this doesn't lead to any problems, right? I mean, if there are like
It
large number of
it does not, because each Go routine takes like 4 kilobytes of stack space, so we can have like we can have quite a few Go routines. But
Okay.
essentially it can lead to some problems, for example in some other queries like shortest path and stuff, in which in which we are essentially traversing a big graph. But that doesn't happen because we are spawning too many Go routines. It's just that we are loading a lot of data in memory to be able to traverse the whole graph.
Okay.
Yeah.
Yeah.
Quick question: is it one Go routine per predicate or one Go routine per group?
It's one Go routine per predicate. So for example, in this query, what would happen is that we would get the initial UIDs, and then we would have one Go routine for name, another for initial release date, another for Netflix ID.
So what if name and initial release date were on the same group? Why would we make two
It,
gRPC calls to the same group?
that's a good point. So like that's something that we could do in the future, that we could be a bit more smarter about it, that we could see if data for different predicates lies on the same machine, and we could do it in the same network call. But we don't do that right now.
Okay.
So we still spawn different Go routines and we make like different network calls.
Okay.
Uh, do we use integer compression while transferring, like sending the UIDs?
I don't think we use integer compression while sending the UIDs. No. So we only use the integer compression while storing the data, and when we are able to like essentially when we read the data, then we kind of like it's compressed, and when we decompress it, but it's not sent across the wire. Like whatever we sent across the wire is just uint64, I think.
Okay.
Yeah.
Pawan, all the nodes inside an alpha group, so do they lie on the same machine, or they can lie on different machines also?
All the nodes inside a alpha group. Could you just clarify that? Like, what do you mean by all the nodes inside
Like,
a
so
alpha?
let's say in the group 2, A4, A5, and A6. So do they lie on the, are they running on the same machine, or they can be running on multiple different machines?
I mean, like they would be running on different machines, because the idea it could like they could also be running on the same machine. It depends on the people running them. But the idea is that if they're isolated, then if one machine goes down, then you can still have another alpha node serve your group.
Okay.
So
So
they would typically be running on different machines. Yeah.
okay, so the query we just saw, so there was no, so group 0, basically zeros didn't do anything. So uh, there was
So
no
yeah.
part of group 0 in there.
No, so zero does something. So one of the things that zero does is that anytime you have a query, it would assign like a transaction timestamp. So zero would assign like a start TS when the query is executed. So essentially, it basically handles out the transaction timestamps. That's one thing that it does. It also does more things when you're doing mutations. Then it would also give you UIDs. So it would give you new UIDs. And then another thing that it does is this information about which predicate is served by which group is also propagated to all the nodes through zero. So the fact that
Okay,
group
yeah.
one knows that initial release date lies on group two, and all that information, and also what is the what's the what exactly is the host name, or for all the nodes in the group two. This information is also propagated by zero to different alpha servers.
Okay, okay.
Yeah.
Thanks.
So this is one thing. I think after this we could do. So what we could go into is we could look into queries with UID or value variables, or we could look into how data is internally stored in terms of data or index keys and how is it fetched, or we could see the actual code in the editor and just go through different bits which are doing this execution. So I'd just like to know what do people think would be most useful that we can do. Any points, like what you would like to see?
I prefer 2 and 3.
2 and 3. Okay. So I think first we can go through 3, because once we have that, then like if in the future someone is working on this piece of code, like like they would also have understanding based on a query where it's executed and what's happening. So I'll just share my screen on the laptop and just go through a bit of code which does this stuff. So essentially what happens is that you could be getting a request, a gRPC request, which would come inside the inside this server query function, which lies in which lies in this this folder EE, like essentially it lies here in this folder. And then after that, uh, we would go into the do query. So for the first step that would happen is that the query would be parsed. The parsing of the query happens, and this function would, for example, here parse the request. It would do authorization if it needs to do authorization, if ACL is enabled, and then it would ultimately process the query. So the major chunk of processing the query happens in the query package, but before that also we do some other stuff, like we assign a start TS, we get like a transaction timestamp, and yeah, so for example, here you can see that if the request did not have a transaction timestamp, we get a transaction timestamp, which we get from 0, and it's assigned to the query. And then we go into the processing of the query. So the processing of the query goes, we are already in query.go. So essentially a query can also have multiple subqueries if you would have looked at some examples. So we would execute all the subqueries that we can. So eventually we come here in the process query function, which lies in query/query.go. And then this is the file which has a bunch of code about query processing. So just to make it clear, when we are in query.go, we are still on the machine which got the request. We'll also see that when do we send the request to another machine for certain predicates that might lie on that machine. So what we are doing here is we are going through all the queries that were part of the request, and we are seeing that what are the queries that we can execute. So some queries might have dependency on some variables, and we might not be able to execute them, but we try to execute the queries that don't have any dependencies on any variable, or a query for which all the variables are resolved. And when I talk about variables, I'm talking about the UID and value variables that are there inside a query. So we are checking the dependency if the query has all the dependencies fulfilled. And ultimately, if all the dependencies are fulfilled, then we go into this function called process graph. And this function process graph is called recursively for processing a query. So firstly, it would be called with the whole query that we have, and then recursively it would be called for other queries. And if you had multiple queries that we can process simultaneously, we would call them in Go routines. So if you had multiple queries, then essentially all of them are called in Go routines to be resolved concurrently. So again, this function has it basically has multiple parts that we can look at. But the interesting thing that I want to point out is that we do some kind of pre-processing for figuring out that we have the right information that we want to send to the server. So like essentially what would happen is we have this structure called subgraph inside the query package, which holds all the information for one particular level of a graph. And then it has like a parent-child relationship. So I'll just go through subgraph. So it has read TS, it has the attribute for which we are executing the query, and then ultimately it has children subgraphs. So in the example that I showed you, there would be a subgraph for the root. Then it would have children subgraphs for name, for initial release date, for Netflix ID, and that can go on recursively. So if you had more levels, then you would have more subgraphs recursively. So if we go back to process graph, ultimately what happens is that we would do some processing and we would be passing around some UIDs from one level to the other level. And then once we are ready to execute the query and process the query, then what we call is, we call this function called worker.processTaskOverNetwork. So as you can see from the name of this function, what we are saying is that we have created a small subtask for one particular level, and for example, this subtask would be like, give me the names of all these entities. So I have these 10 entities and give me the name of all these entities, and name might lie on a different server. So we would just call this function in worker, and this function, what it does is it checks that if I have the data for this predicate, then I'll just get the data from Badger where it's internally stored and return it. Or I would call the I would essentially call some particular alpha server on a group on which this data lies, and then from there return it. So the interesting thing is that that essentially whatever we are doing in query.co was happening on the machine that received the request. But in the worker package, when we call process task over network, that might be making a network call. It might not be if essentially whatever predicate I'm requesting lies on the machine that got the request. Otherwise, it might be making a network call, and ultimately it would return me the data that I asked for. So that's kind of like I mean, it's like a top level view of how a query is executed. That you would have the parsing that would happen. Then we would do the processing in query.go, and for all those individual subtasks for essentially getting for getting data for one particular predicate, we would call worker.process_task_network. So worker has all the code which would be making the gRPC calls to other alpha servers and getting the data and stuff like that. And as you can see, for children, what we do here is we execute them in Go routines. Just a second. So while we are going through the children of a subgraph, we execute them in Go routines, and then we use channels for getting back the result, and then essentially just aggregating the result, all the result that we got from different machines. So all the result is aggregated on the machine that got the request. It's just sent to different servers for processing. Any questions here? Even if you have any other questions that came to your mind earlier and you want me to go through those particular pieces of code, I can do that.
What if the client sent the request to an alpha where even the root, like in your example, the name predicate does not belong to that group?
So in that case also, what would happen is, again, we we would be creating like a subtask, like we would be creating a task, and again the process task or network would be called, because this function process graph is also called for the root. So first it's called for the root, and if the root doesn't exist on the machine, then again I mean, like it doesn't matter if that root predicate exists on the machine or not. We would still call process task or network. In the worker package itself, we would see if we serve this predicate. If we serve this predicate, then I would get back the results. Otherwise, like essentially a network call would be made. So this function is called for the root itself. So the result is resolved for the root, and then we call it for the children.
So does the aggregation of the query happen on the initial alpha that it hit, or the first alpha which has the root?
Yeah. So what would happen in that case is, say I am say basically I got a request from group 2, and group 2 doesn't serve name. So I would create a task for getting the data for name, and then I would call process task over network for getting the name. And all of this is happening on group 2, but ultimately group 2 would send a request to group 1 for resolving that filter, which says that give me like essentially give me all the movies which had Blade or Runner in them. And then group 1 would send that data back to group 2, and then again I would be back here. So again, all the aggregation would only ever, like it would always happen on the group that got the request, which in this case might be group 2. But to resolve the root, it might be calling a node on group 1.
Okay.
So yeah, I mean, like we could be going over the code in worker. It's a lot of code, so I don't think we'll have enough time to do that. But the main point to note here is that all the aggregation happens on the node that got the request, and all the aggregation is happening in query.go. And then like essentially anytime we have to resolve a task, we send it using this function called process task over network. And when we are talking about task, we are talking about things like getting the name or getting the initial release date or getting the friends for a list of UIDs. So all those things are sent in this thing called task, which is there in the protocol buffer definition that we have. So this is something that some of you would be aware of who have worked with the query package. So this is how we say that for a bunch of UIDs, give me the value of the attribute. Yeah, so that's what you do here. So you would be encapsulating that information here. So yeah, and then you would get back the values for a list of UIDs. So I think what I can quickly do here is I can go back to sharing my iPad because that had more data to see. And then if you have any more questions, I think we can ask those. Otherwise, we can, yeah, we can probably just cover this bit. There are we basically have a lot of things that we could cover in the query package, but this is the initial introduction that I wanted to give. And then later we can go into how sorting happens, how filtering happens, how value UID variables are resolved, but those things would take their own time. So I'm not doing that as part of this.
Pawan, I have a question. So you mentioned that only one alpha gets the request, right? For instance, group one receives the request, and to resolve director.flim, it sends a request to A4, right? So
Yeah.
let's say A4 is not available for some reason, but that group is still
Yeah.
healthy, right? So what happens in that case? You said that we send request to only one alpha node. So if I do that, then that means
Yes.
I would say that this is not a healthy cluster or whatever, but then it's still a healthy cluster, right? So
Yeah,
what
it's
happens in
it's a very
that
good
case?
point. So we also do this thing that from group one. So actually what I said was not exactly correct. So from group one, we would send a request to say A4, and if that request doesn't resolve in 10 millisecond, I think we send a backup request to another node in the same group. So we would, if the first request doesn't resolve in a particular time, I think that the number is 10 millisecond, but I'll have to go and check. Then we send the request, we send a backup request to another node in the group, if we can find that. And then essentially whichever request resolves, we just use that to send the data back.
And
That's a good
if it's
question.
a slow request or a slow processing request for some reason, you'll send the same request to all nodes in that group, right? As in, if let's say there are three, so even none of
No,
them
we would
return
not.
back in.
So we would just send one backup request. We don't send it to all the nodes. So if both of them don't don't resolve after a timeout, we just do a timeout.
Can I have 5 nodes in a group? Is there a way to configure that a group can have
Yeah,
5 nodes?
yeah, you
But
can
in
have
that
any
case,
number of nodes.
we would again be saying that if let's say you just accidentally or maybe in a wrong way sent request to only the 2 nodes which are not available, but still the group is available. So again, we would be giving a wrong indication, right? That group is not available even though it's available. So maybe we should, yeah.
Yeah, we could look into seeing. I think like initially when we decided to do this, it was based on some research that if you like essentially if you just it's like I think we probably read a paper by Jeff Dean, and in that it was recommended that if you send a request to one backup server, then these many percentage of requests are resolved in correct time. So we could again look into experimenting with sending it to a majority of nodes if any of them don't resolve. But yeah, again, it's a good point that we could look into.
Oh, also, how does group one know which nodes are healthy in group two, right? As in zero has this information, zero stores all this, right? But then
Yeah,
group one could have steal information, as in something happened in group two, but group one does not know.
yeah.
So then does it send or maybe confirm with zero before sending a request, or does it just use the local information it has?
It just uses the local information, but there is a request that is made. So it's like a ping request that's made between all the alpha servers to check the status of other alpha servers. So for example, A4 would have a connection to A1, A7, all of those, and it would be regularly checking the connection and checking if the connection is healthy. So it has some interval in which I don't know, I'll have to check what's the exact interval, but it's like a gRPC echo request that's made regularly to check the health of all the other alpha nodes. Because as you said, like essentially alpha node would only get that information initially from zero, that what is the what's exactly the host name of other alpha nodes, but then it does all these check locally to check if the node is still healthy.
Also, doesn't zero stream the membership state every 1 second or something?
It does that, yeah. It also streams the membership state. So
So
if one of the zero,
yeah, if one of the alphas are unhealthy, zero will figure it out and send it out within the second, right?
yeah, so that would also happen, but you could also
Right.
have the case of a network partition between, say, alpha and the zero, and something like that would be caught by checking this echo request.
Okay.
But yeah, if you had like alpha node that was removed or added, then all this information is propagated to zero,
Right.
to all like by 0 to all the alpha. This thing itself could make for a whole talk about how the membership information is propagated and what are the different kind of things in the membership that we could propagate. Like for example, if you're assigning UIDs and if you're assigning transaction timestamps, or if an alpha node is added or deleted, I think it could make for a whole talk in itself.
Right. Yeah. Also to add to Pawan, I think for queries you can go to any group, but for mutations you send it to any member of the group, but then you have to go to the raft consensus to make a proposal, and that's a change in state and all of that. It's a different talk.
Yeah, exactly. Any other questions that we have at this point? Okay. One more question I have is that like it's mostly to the people who are new in the company. Like after listening to this talk, were there any things that got more clarified or something, or did you already know about this? Or so it's mostly people who are new. Did this talk increase your understanding of how the query thing works, or you already got it from the paper or other places? If there's nothing else, I think we can just call it an end here, and then we can do another walkthrough sometime else about what happens in mutations or what happens inside worker and the membership information and stuff. But yeah, that's pretty much it that I wanted to share for today.